This is a brief explanation of the binomial theorem. Consider the fourth power of a plus b. It is a plus b times a plus b times a plus b times a plus b. I represent it in different colors. The expansion consists of many terms. Look that we can take out this a, this a, this a, and this a, and multiply them. We will have this term. This is a to the power 4. Or you can take this a, this b, this a. Then we will have the terms a, b, a here. It is a cube b. Look that in this line, the terms is a to the power 4, and in this line there are totally 4 terms. The 4 terms are all in a cube b, and for this line we have 6 terms all in a square b square. And here we have 4 terms that they are a b cube, and for the last line we have b to the power 4. So we have a to the power 4 plus 4a cube b plus 6a square b square plus 4ab cube plus b to the power 4. But why do we have these coefficients? We have to do some counting works. For example, for a cube b, there are 4 positions, and we have to take only 1 position for b, so the number of terms that are in a cube b is 4c1. We take 1 position from 4 possible positions. And for a square b, there are totally 4 colors here. We take 2 colors to place b, so the total number of possibility is 4c2, so we have 6 times a square b square. We have totally 16 terms in the expansions, and each term is the product of 4 variables. So we have the sum of the indices of the expansions is always equals to 4. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, and 0 plus 4. And 4, 0, 3, 1, 2, 2, 1, 3, and 0, 4 covers all the possible combinations of the indices. And for the coefficients, the coefficient is just the numbers of possibilities that we have the term. For example, a square, b square. These are the number of possible terms in these expansions that will give you 2b and 2a. And the number of such terms is 4c2. So we have this binomial theorem. Now I'm going to explain the Pascal triangle. The Pascal triangle is easy to construct, and it gives the coefficients of the binomial expansion. Why does the Pascal triangles work? Take a look at this example. Here I want to multiply this polynomials by a plus b. All the terms of these polynomials are in degree 3. This is a cube, this is a square b, so the sum of the indices is 2 plus 1 is 3. 1 and 2 is 3, and this is also in degree 3. So all the terms are in degree 3. When we multiply this by a plus b, I first multiply it by a. I just copy the coefficients and raise the powers of a by 1. And then I have to multiply all the terms by b. Again, I just copy the coefficients and raise the power of b by 1. Next, I will add up all the like terms to obtain the final answer. Here, this 2 is just this 2. This 4 is just this 4. And we have 3 here. 3 is 1 plus 2. Minus 2 is minus 3 plus 1. 1 is 4 plus minus 3. If I apply the method of constructing the Pascal triangles on the coefficients of this polynomial, then we will obtain 2, and 2 plus 1 is 3, 1 plus minus 3 is minus 2, minus 3 plus 4 is 1, 4 I just copy here. Then these numbers are just the coefficients of the product. The construction of Pascal triangle just gives you a way to multiply such a polynomials by a plus b. Here we have one more example. These polynomials are polynomials in AB such that every term has degree 3, a cubed, a squared, b cubed. We can use the method of construction of Pascal triangle to find this product. Here I write 4, 2. Because the term in AB squared is missing, I put a 0 here, and minus 1. And to multiply this by a plus b, I just construct one more layer here. And then to multiply it again by another a plus b, I do it again. And finally, multiply it by a plus b the first time. We have the highest power in a in both the polynomials are in a cubed, so the products must be a polynomial up to a to the power 6, so we have the answer. This gives us an easy method to do such kind of multiplication. The binomial theorem tells us that the coefficients of the expansions of the nth power of a plus b are just NCR. But we also know that the Pascal triangles give the coefficient of the binomial expansion. So the binomial coefficients NCR must be related to the Pascal triangle. Actually, the relations relies on this identity. Note that we have NCR minus 1 plus NCR equals to n plus 1 CR. So for example, we have 4C2 plus 4C3 equals to 5C3. And you can find this addition in the Pascal triangle here. 4C2 plus 4C3 is 5C3. 5C1 plus 5C2 is 6C2. You can find it here. And all the numbers on the side here, NC0, are all equals to 1. And on this side, NCN are all equals to NC0, that is 1. This gives us another way to explain the binomial theorem.